Hello, Professor. Hello, TAs, and any students that may be watching. Thank you for joining our presentation. My name is Preston Tidwell, and this is Encore Vaish Ampayan. And we're going to be talking about 3D printed heat sinks that are directly attached to CPU dies. So a little background on these. On computer chips, thermal dissipation is quickly becoming the limiting factor in computer chips. And that is because processors are becoming denser and denser, and their power requirements are increasing. And while the efficiencies are also increasing, because of the power requirements are increasing, the heat is also increasing to a point where it's becoming the limiting factor in these chip designs. According to Moore's law, who was an engineer for Intel in the 70s, he said that every 2 years the chip will essentially double in the number of transistors, meaning that it gets twice as dense. So, which you can in turn means twice the amount of power in the same amount of space, which just means you have more heat that has to be pulled away from the chip. So traditionally how these heats are cooled is that the die, which you can see here is a little cross section in this diagram, the X pattern section in this diagram is covered in a thermal interface material along with the heat spreader, and heat is transferred through these two materials into a heat sink that would be on the other side of the heat spreader that transfers the heat as far away from the chip as possible. And so what these two layers cause is a resistance between the die and your heat sink. So they're by our theory is that by reducing these layers we can improve the heat transfer effectiveness. So what we looked at is directly 3D printing these pins on top of the chip. And we looked at designs from M. Conrad, and this is the paper that we based all this on, and he looked just at a metal pins, but we also looked at ceramic and polymer materials. And Encore will go in more in depth later about those specific materials. But in his original paper, what they did is they actually 3D printed these pins on either side of the chip, and there was a thin metallization layer applied to the chip on both sides, and a thin layer of solder before the chips were printed on there using the SLM process. And those two layers the metallization help protect the chip, and the solder will help adhese the pins to the chip. So some of our assumptions for this is that we assumed 5 watts of heat being evenly emitted across the surface, meaning it's a single core chip. The solder and the metallization layers are considered thin enough they can be neglected for the heat transfer. Additionally, the pins are dissipating heat through forced convection through air. More or less, it's simulating a fan blowing air on them. Just to mention that in the paper that we looked at, they used in oil being forced through across the pin, so they will get a higher heat transfer rate than we get. And here's the simplified design that was mocked up in SolidWorks. And now Encore is going to go in and talk about what it looks like in Abaqus.
Hello. So as Preston had mentioned, we created the solid parts in SolidWorks, and then we saved them in IGS format, and we imported them in Abaqus, where we assembled them. And this is an image after meshing and assembling all the parts. Some of our assumptions and boundary conditions were that we assumed a fan is installed on top of the heat sinks, as is the case in the traditional CPUs. So there is forced convection on the fins and around some of the base of the top part of the die. The sides of the die emit heat through natural convection, and the base, which acts as the PCB, which acts as a heat spreader. Instead of considering the heat being conducted to the CPU cabinet on which it is mounted, we assume to be natural convection, and it has a very low heat transfer coefficient. For contact conditions, we assumed we specified contact between the die and the PCB, and from the die to the base of the pins, so that heat conduction is carried out during that. We considered three materials: metal, ceramic, and polymer. For metal heat sinks, we considered the aluminum powder, which was mentioned in the previous paper. These fins can be printed on top of the die using the SLM method. The properties of these pin fins will not be as good as the conventional method of manufacturing the aluminum material, but the advantages of this process is that high aspect ratio pin fins can be created, which is really difficult using the traditional manufacturing methods, and we can directly 3D print it on top of the die, reducing the thermal resistance offered by the thermal interface material and the heat spreader. These are the results of our simulation. The simulation showed that the chip had around 80 degrees of temperature, and the fins had a 72-degree temperature, which indicates that the fins are taking away heat from the chip to the top of the fins, which is conducting the heat. This is the video of the transient analysis. The analysis runs for we considered the analysis to be running for 5 minutes, and it shows that it reaches steady state after around 2.5 minutes. Going back, for the ceramic heat sinks, we found a company called 3D Sum, who actually manufacture ceramic heat sinks. They use aluminum nitride for its high thermal conductivity, and they use SLA method for manufacturing ceramic heat sinks. After running the simulation, we found out that the chip temperature rises to around 90 degrees C, which is hot, but it can be withstand by the chip. The fins are extracting heat, they are hot, which indicates that they are conducting the heat. This is the video for ceramic pin fins. You can see that again the heat is being conducted. The chip is around 90 degrees C. And the last part, the polymer heat sinks. We know that it's not ideal to have polymer materials at heat sinks as they have a very low thermal conductivity. We found a company called TC Poly who actually manufacture polymer heat sinks. They just mentioned thermoplastic elastomer as the patent for that product. It's still pending. It has thermal conductivity of 8 watts per meter Kelvin, and they use fused deposition modeling for 3D printing. And these are the results for polymer heat sinks. From the simulation, we can see that the fins do not carry the heat and they are relatively cold. So they are really not a good choice for heat sinks. So our conclusion is that metals offer best performance for the three materials that we assumed. It's really useful and advantageous as we can manufacture complex and high aspect ratio pin fins, and we can directly 3D print it on top of the die. Ceramics can offer promise as we can use them for liquid cooling applications, especially when we use dielectric liquids and they might corrode the metals, but ceramics can be used in such cases, and polymers are really not a good choice for heat sinks. To make the simulation realistic, we need to consider comparing our simulation with a simulation considering traditional die chip thermal interface material heat spreader assembly, on top of which there will be a heat sink, so that we can accurately compare the results of the two simulations and see if what method we are proposing is it really feasible or not. Thank you so much. These are some of the references that we used, and thank you so much for listening. If you have any questions, please let us know.